day 12. Day 12. So we're going to be talking about mutations, evolution, and natural selection. Okay, so let's start by talking about mutations. So let's draw out some DNA. Let me make sure this mic is on. Okay, good. Okay, so let's start by drawing out some DNA. So 5 prime, A, T, T, C, A, T, G, A. Sure. The other one, T, C, A, T, G, A, A, T. Okay, so here's my original strands of DNA. Remember, they're held together by these hydrogen bonds. Okay, and now we're going to copy this DNA. So let's split this apart. Act like RNA polymerase to make new strands of DNA. So I'm going to use this top one as my template. So I'm going to go right to left. So T, C, A, T, G, A, T, 3 prime. Down the bottom here, 5 prime, A, T, A, T, G, A, 3 prime. Okay, so now I've been DNA polymerase, and I've copied the DNA. And now a second DNA polymerase is going to come through and check it and make sure I didn't make any mistakes. So I'm just going to do this by adding my hydrogen bases, or my hydrogen bonds between the bases, which it would have done already anyway. Here, so here I've made an error. Okay, let's make sure I didn't make any other ones. Okay, so here I've made an error. Now, I don't know which one was the original. I don't have that other strand to look at anymore. So I'm just going to say, you know what? I think I'm going to change this one to be a T so that they match up properly. Okay? So this right here, what I've introduced, is called a mutation. And mutations can be good or bad. And we talked about mutations before, right? And part of the things that we talked about was that mutations are always going to be random, right? And that mutations can happen in regulatory regions, like switches, right? They can happen in promoters too. And they can also happen in those coding regions, right? And have different impacts depending on where the mutation happens. And then we can also have them in somatic cells, so that's regular body cells, or in germline cells, and I don't think we've said this word before, and these are cells that can be inherited. Okay? So this mutation could happen in my skin and maybe cause skin cancer, okay? So that would have happened in the somatic cell and it would only affect me. Versus if it happens in a germline cell, then it would have an impact on my daughters, right? It would have had an impact on my daughters if it made the egg that made them, right? So mutations do happen. They can be good or bad, but they're always going to be random. So I would love it if I had 2 sets of arms. That would be amazing. Maybe I couldn't choose that for myself, and I can't choose that for my daughters either, okay? I can't be like, hey, body, why don't you make like another set of arms? That would be great. I can't just want that for them and then have it happen, right? So they're random and they aren't due to any external pressures or anything like that. They can happen because of external toxins or environmental impacts, and you'll talk about that more in genetics, okay? But where they happen is still going to be random, even if the reason why they happen is due to the environment. Okay? All right. So here we have a mutation, and mutation by itself can cause evolution. So let's do a definition of evolution first. So evolution is the change in allele frequencies in a population over time. Okay? And the example that I like to use a lot for this is actually by using ladybugs. So let's make some ladybugs. I'm going to color them in. Should do cicadas because they're all around me right now. Okay, so some ladybugs. And let's say all these ladybugs have 2 spots, okay? So we have 2 spotted ladybugs, okay? And I'm just going to copy this one, make a whole bunch of copies. Okay, and let's say that all of these ladybugs have this version, okay? Oops, this version here, okay? So this, and let's call this version little a, okay? So this little a version is in all of these insects, and this is going to be a diploid. Insects are diploid, so they get a copy of their DNA is from mom, and then a copy of DNA is from dad. So all of them are little a, little a. Okay? So in this population, I have 100% little a. Okay? So 100% of my individuals are going to be little a. And these ladybugs are going to group together and make offspring, okay? And when they make offspring, the females in this case are going to make the eggs and the males are going to make the sperm, okay? And let's say that there's a mutation that happens just in one of them. So that mutation that I showed above is going to happen in just one of these little insects, okay? So here I have a new mutation that has happened just in this one right here, okay? And so one of her eggs gets this mutation, this little a, or sorry, this big A. So one of her eggs is going to end up with this mutation. Okay, this big A. Where's my pen? Okay, just one of them. Because mutation happens just to in the one, and then we go from there. Okay, so now we need to make all the rest of the egg and all the rest of the sperm. So maybe she gives that capital A, but she also gives another one that's a little a, and the sperm from this other little ladybug is little a. Okay, so, and then the rest of my population is all little a. So little a eggs, little a sperms, so when these join together to form zygotes, okay, and we're going to talk about this more next week, about the process of how we got these eggs and sperm, and then the process of fertilization, we're going to end up with individuals that might have a different genotype than what we had before. So this one is going to have little a, right? So it's going to look just like the parents. So little a. Just put that in right there. This other one right beside it, though, has one big A and one little a, right? So let's say that this big A actually encodes for 3 dots, okay? So instead, this individual, instead of only having those 2 dots, maybe has 3 dots on each side. So 1, 2, 3 dots on each side. Let's go back to that blue, right? Oops, I didn't mean to make its head different too. Okay. And everybody else is going to have the little a, little a, little a, little a, little a, little a, little a. So just copy one of these. Oh, I don't need those extra legs. Okay. So that one's that. This one is that. Little a, little a. Little a, little a. Okay. so all the rest are little a's. So I can look at my population and be like, okay, well, how many little a's do I have now? So you can count them and be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 are little a, and 1 is the big A, right? So if you end up doing out this math, right, we can figure out what our percentages are, okay? So let's just go, I'm gonna do easy math for you guys when you do this, okay? But you will do 1 out of the 12, right, is going to be 0.08, is going to be the big A now, okay? So the big A is going to be 0.08%, or 8%, sorry, I did doubled. Okay. Move it over. Okay. So 8% is going to be your big A versus 92% is going to be your little a, okay? So that's what we have for our allele frequencies in the population. Now, evolution is the change in allele frequencies in a population over time. So here we have a change in allele frequencies from 100% little a to 92%. So here we've had a change in allele frequencies. Okay? Okay, so we've had a change in allele frequencies here. So this is evolution. Mutation alone can yield evolution. Or evolution can happen because of mutation alone, right? Can cause, maybe. Let's do that. That's better. Okay, mutation alone can cause evolution, and we just showed you right there. Okay, now let's play with this idea of natural selection. So here in this individual that has the 3, maybe it's better to have 3 spots than 2, okay, for whatever reason. So maybe that confers a fitness advantage. Maybe in the next round, the ones with 2 spots are like, ooh, I really like that 3-spotted one, okay? Maybe it helps them hide from predators, who knows? For some reason, there's a fitness advantage, okay? So an individual with more spots, in this case, might have a higher fitness, okay? So let's draw out a little graph here. And in this case, we've got the number of spots in the parents, okay? So that's on our x-axis. So I like to think of the x-axis like an ox, you know, like the animal on ox. Can I draw an ox? Oh gosh, okay. Like an ox. This is an ox, guys, with horns, maybe. Okay, it looks like an insect. Okay, I cannot draw an ox. I'm not even gonna try. Okay, like think of it like an ox. It's horizontal, okay? So it's horizontal like an ox. Versus the y-axis is here. And I like to think of this like a yo-yo going up and down, right? So here's my yo-yo going up and down, right? And so on my x-axis, I've got my number of spots in my parents. On my y-axis, I have number of offspring. Okay, so let's say that all of the insects that have 2 spots have, I don't know, 2 offspring, okay? Versus, so 4 total. Versus my ones with 6, okay? So all of them have 2 offspring. Versus my ones with 6 have 4 offspring. Okay? So maybe I already have a population that has 4-spotted individuals and 6-spotted individuals, and I have something like this. Okay? And so here you can also have lots of different variation. Maybe there's 5 or 7 or 8, right, number of spots. So you've got something where you have the number of offspring here is correlated with some trait in the parents. So here we have more spots is better. So fitness is a measure of offspring, okay? And higher fitness equals more offspring. So in this case, we would say individuals with more spots have higher fitness. Okay? Okay, so then the other thing that we care about is whether or not the offspring actually get the trait or not. Okay? So here, we're going to have, again, the number of spots in parents. Okay? And on the y-axis, we're going to have the number of spots in offspring. Now, we already know that this is heritable because we had introduced this mutation and that's what yielded this other change, but we don't always know this. So we're always looking for a graph that shows that the number of offspring in the parents is going to be the same as the number of offspring, or sorry, the same trait in the offspring. Okay, so here the number of spots in the parents, if you have 2 spots in the parents, you have 2 spots in the offspring. If you have 4 spots in the parents, you have 4 spots in the offspring. If you have 6 spots in the parents, you have 6 spots in the offspring. Okay, so you're looking for a graph that looks like this, where you have the same number of, or the same trait in the parents and in the offspring. Okay, now if you have an intermediate trait where you know, like we could have a 3, you know, and we have a 2 and a 4 coming together, then maybe we would have something that's a 3 for the offspring. So it's the average number in the parents versus the average number in the offspring usually. Okay, so here is my trait is heritable. Okay, so the we can predict, maybe let's do it this way. The trait in the parents dictates, why can't I spell that? Dictates what we see. So determines. What we see in the offspring. Okay, so here we have a few different things where we see fitness, right? We see heritability, and there's one more trait that we need in order for evolution by natural selection to occur, and that is variation. Now, in both of these graphs, you can see variation. So you can see different numbers of spots in the parents in both of these, okay? So the last thing that we need for natural selection to be able to occur is variation. And you can see this in both graphs. Okay, so if we have all 3 of these things, differential fitness, heritability, and variation, natural selection could occur. Okay, so natural selection, which is one mechanism of evolution, can occur if we have variation, that variation is heritable, and differential fitness. Okay, so those are the 3 things that we need for natural selection to occur. Now, we do need both of these graphs in order to determine that, because this graph right here on the left, this graph will tell us only about fitness and heritability, versus this graph over here, fitness and variation on the left, right? So this graph over here tells us fitness and variation. I'm not sure what I just said. Okay, fitness and variation. This graph over here on the right tells us about heritability and variation. So both of them can tell us about variation, but only the graph on the left can tell us about fitness, and only the graph on the right can tell us about heritability. Okay? And for natural selection to occur, we need all 3 of these things. So let's play with an example of this and how we can look at natural selection in an environment. So I came inside quick because I need to get my beans. So I'm going to grab some beans and I will meet you back out in the garden in just